Okay, so let's get started. A few more things about the wind fixed coordinate system. So this is your airplane, and let's say this is V infinity, right? And xw is in this direction. And zw is like that, and yw is like this. Okay? Why is this coordinate system so important? Who would make use of this coordinate system the most? Aerodynamics. Why? Because of a number of things. First of all, what is the definition of lift and drag? How do you define lift? What is the direction of lift? What? Just say it one by one. Raise your hand and say one by one. What is the definition of the direction of the lift? Yes, please. Okay, so lift is always perpendicular to V infinity, which means lift is always opposite in the direction of ZW. Or if ZW is pointing upwards, it would be in the direction of ZW. But it's in the line of action of ZW for sure. Right? So that's why this is so important. And drag is always in the direction of XW. I mean, in the opposite direction of XW. So that would be drag, because XW is parallel to V infinity, so is drag. So they are all in the same direction. So the definition of lift and drag is actually based on this wind fixed coordinate system. Now think of our other example where this is my airplane. This is V infinity coming from the side. And let's say this is XW. And this is YW. What is the direction of drag? It's here. This is your direction of drag. It is parallel to V infinity. Now the picture you see in aerodynamics books is often a 2D picture. But note that we are doing now here a 3D picture. V infinity could come from the bottom, like this. It could come from the top. But at the same time, it might come from the sides. So it could very well be a combination of them. So V infinity could be like that. Check out this airplane, and this is my V infinity. If you're flying forward with an angle of attack, so this is the picture you see in aerodynamics books, right? V infinity airplane, so it's like that, and this is your angle of attack. But you might be flying like this, with an angle of attack, but a little bit to the side, which means V infinity will be this, plus your side velocity, so it will be like that. So V infinity could be looking like this. Okay? In that case, XW would be pointing this way, V infinity would be like that, drag would be in this direction, and lift would be perpendicular to that. So it would be, if this is that, so lift would be kind of like this because of this angle. It would be perpendicular to V infinity and therefore perpendicular to XW. That would be lift. And drag would be in the direction of V infinity, opposite of course. So opposite to XW, minus XW would be the direction of drag. Is that okay? So it could be like this, like this. What about an airplane flying backwards? It can't fly backwards really, but it's falling backwards. So V infinity would be coming from here, and that would be XW. What if an airplane is falling down like that? This would be V infinity, and that would be XW. Understand? Airplane falling down like that. Where is V infinity? The air particles are moving towards the airplane, When you fly like that, relative to the airplane, the air particles are moving like this. Therefore, this is V infinity, and therefore xw. Where is drag? Drag is this way. It's quite weird. Okay? It's not always that pretty picture. It could be also like that. This would be drag, strictly speaking. Understood? Okay. One more thing. What happens if there is no V infinity? No, you're on the ground sitting and you are not moving. What happens then? Can you define the wind axis coordinate system? No. The answer is no. When you're on the ground, no air, no wind, nothing, you can't define wind fixed coordinate system. Another example. Think of a balloon that is up in the air and staying in the air, a balloon. If there's no wind, can you define a wind axis coordinate system? No. If there's no V infinity, you can't define a wind fixed coordinate system. Think of a helicopter. Now that's an interesting one. Think of a helicopter hovering in air. Hovering, which means it is staying in air, not moving left, right, just staying in air. Is there a V infinity? Where? No, not on this rotor. I'm meaning on that helicopter, the whole helicopter. Is there a local air velocity? No, right? Because it's staying in the air, so it's not moving left and right. I mean, you might say there might be air movement because of this, but that's not what I'm talking about. I'm looking at the whole airplane, and I'm looking at movements with respect to the atmosphere. Okay? So, there's a whole airplane. Is it moving left and right? No. So there's no V infinity. Here's the funny thing. If the helicopter starts moving forward, you will see a V infinity from this side, if it starts moving forward. If the helicopter decides to move backwards, V infinity will come from that side now. You see? Airplane moving helicopter, look at me. Helicopter moving forward, air is blowing from the front with respect to the helicopter. You move backwards, suddenly the air particles seem to be moving towards the helicopter, isn't it now? So V infinity is now this. Now think of a helicopter going this way. Yes, V infinity is here. Moving forward, V infinity is coming from the front. So XW is pointing this way because V infinity is coming from the front. Helicopter moving backwards, V infinity is coming from the back, therefore XW is pointing backwards now. Understood? Think of a helicopter in hover and doing this. What's happening to V infinity? Forward, backwards, forward, backwards. What happens to XW? Forward, backwards, forward, backwards. So the whole coordinate system is jumping to one direction and then to another direction. So XW, I mean this wind fixed coordinate system would not be a very good idea to be used in a helicopter in hover because it would change directions all the time while it is moving. Now a helicopter doesn't only move backwards and forward, it can only move sideways. So if the airplane is moving sideways, which way is V infinity? This way. This way, V infinity is coming that way. If the helicopter is moving sideways, this is XW. Which way is drag? That way. Okay? So think of an airplane in air, of a helicopter in air, hovering, and the helicopter is trying to keep its balance and is doing that. At each moment, V infinity is changing direction, and so is the wind fixed coordinate system. It's changing direction. So it is not a very good idea to use wind fixed coordinate system for a helicopter that is doing this kind of motion in air. Understand? But for an airplane that is flying in air, doing maneuvers and things like this, it's a very useful coordinate system because we define lift and drag. And you understand that the direction of V infinity is everything that an aerodynamicist would need to calculate lift, drags, and moments and things like that, angle of attack, side slips, and all this. So therefore, this coordinate system is very, very important in terms of the aerodynamics. If you look at the vehicle carried coordinate system, it's not exactly true because this is pointing towards north. So the aerodynamicist is not really interested too much of this coordinate system, for instance. This is just to show the orientation or show other things. But the wind fixed coordinate system is quite important, especially in aerodynamics. So, do you have any questions on this? Is this clear now? Sometimes it is not very intuitive sometimes when you say an airplane is falling backwards and the drag is forward, right? But you have to now try to think in a 3D manner, which probably maybe you didn't do in other instances, right? Okay? Any questions? Good. So fifth coordinate reference frame, and that's the most important one really, but it's the most easy one to after we have made the talks in the past weeks. It's the inertial frame. We call it Fi, so this is what I call the the inertial frame. And we can, of course, also have the inertial fixed coordinate system. Well, you know, we have already talked about this. This is my Earth, right? And we have distant stars. They seem to be fixed. We don't know if they're really fixed or not, but we assume they're fixed. So we can define a coordinate system anywhere we want. Xi, yi, zi, that needs to be fixed with respect to distant stars. So O, X, I, Y, I, Z, I, that is my coordinate system, is fixed with respect to distant stars. So this is the ultimate coordinate system that is fixed in space. Now this origin, you can put it anywhere you want, of course. You can put it here on this point on Earth. However, as soon as the Earth starts moving, the inertial frame has to stay fixed, which means we can't really attach it to the Earth. The Earth is moving, so the inertial frame is the ultimate frame that's not moving. Everything else moves with respect to the inertial frame. So we can't really attach it to something. The only thing I can attach it to is in space that is defined by distant stars which appear not to be moving, which is again another assumption really. Maybe the distant stars, we are all moving in the universe. I mean, you know, these are things that we don't really know. However, basic assumption, the framework, the Newtonian physics, the framework of Newtonian physics rests on the assumption that there are distant stars that are not moving, and that is the ultimate inertial frame. And the formulation F equals ma is only true in this framework where this acceleration is defined with respect to that inertial frame. So never forget that. Okay? And this is like 101 physics. You can't really, if you miss that, everything else doesn't make sense. Doesn't matter how good you can calculate lift and drag. I mean, you have to understand this part. Understood? Any other questions? Okay, number 6, I will not make the definition now, we will do it later. It's called the stability frame, stability frame of reference. Or we call it sometimes, there's a coordinate system, it's an important one, stability axis system. And we'll talk about this later, because I need to make a few definitions before I explain this one, but just have it here. We will talk about this later. Okay? So this is the end of the definitions of reference frames and stability coordinate systems. Any questions of any of these? So to summarize, we have the body fixed coordinate system. Look up here. The body fixed coordinate system is attached to the airplane, moves and rotates with the airplane. So it's like that. Look up here. It is attached to the airplane, moves and rotates with the airplane. That's the body fixed coordinate system. The vehicle fixed coordinate system is where x is pointing towards north. So this is your coordinate system. So that it is attached to the airplane. So it moves with the airplane, but it's always pointing this way. Okay, x towards north. The coordinate system. That's the vehicle carried coordinate system. So the vehicle carried coordinate system is the airplane might be rotating, moving in any direction. It's always pointing in one direction. That's the vehicle carried coordinate system. The earth fixed coordinate system is attached to the earth. X is pointing north. Z is towards the local gravity vector. So you can move like that, and this is your coordinate system. And then we have the earth-centered coordinate system. And then we have the wind fixed coordinate system attached to the airplane, always points towards V infinity. These are all coordinate systems that we are going to use in one way or the other. And then there's the inertial coordinate system, which is fixed to the air, to space, with reference to distant stars. Okay? Each one of them is one by one really a reference frame. However, some of them are very useful, some of them are not useful at all. But to each reference frame, we can attach a coordinate system. Again, sometimes the coordinate systems are very useful in certain cases, not useful in other cases. But we need to understand the definitions by heart. By heart means very accurately, not so-so. Because then we can start talking about things. Okay? Any questions? Yes, please.
Which one of these reference frame is best for the helicopters?
They are all useful in certain cases, in certain situations, for certain purposes. You cannot really pick one coordinate system or one reference frame and say, this is good for this vehicle and the rest is not good. You can't really say that. They are all serving a certain purpose. And as this class progresses, you will understand probably a lot better what their purposes are. Okay? Yes?
So, I'm confused about the helicopter.
Example?
Yeah,
Okay.
because I'm thinking, right now we are, for airplane, we are getting the lift V-infinity, but for helicopter, we are getting lift from rotor, and V-infinity is because of the rotation of the blades.
That's right. So the helicopter, I don't want to confuse you with helicopters. You're right, the definition of lift, or the way we obtain lift, is a bit different on a helicopter. Strictly speaking, if you want to look at the lift generation of helicopter, you should not be looking at the whole body. You should really take this one blade that is rotating and look at the local wind axis of this little airfoil. Take this airfoil, look at the V infinity of this airfoil, and then define lift and drag for this airfoil on the rotor, and then add up everything and say this is the lift vector. Okay?
So can it be the wing fixed frame?
Yes, this will be the local wind axis system for this airfoil. But the airfoil is only 2D, so you only have two directions, so you need to take this component. So this was not a super good example. In other words, it kind of confuses you. But when we look at the whole airplane, Helicopter. The helicopter doesn't generate lift based on the body, but on these rotating wings. So you need to calculate the lifts over here. You're right, in other words, lift here is not perpendicular to xw. That would be not a good definition for lift for a helicopter. But you can still define wind axis coordinate systems. Is that good? Any other questions? In this class, don't worry, we will not talk about helicopters. I have a different class for that. Okay? Here we are only talking about fixed-wing airplanes. The helicopter is just a good example because it can go back and forward and sideways. And the XW, if you want to define it with respect to V infinities, keeps changing. A balloon is also a similar example, really. Any other questions? Okay, so now we are at an important point where I will do one more set of examples, definitions, I'm sorry. Some important symbology and definitions in the body fixed coordinate system. Some important symbology and definitions. Okay, that's really bad, sorry. Some important symbology and definitions in the body fixed coordinate system. Let's do it like this. Some important symbology, comma, and definitions in the body fixed coordinate system. Okay? So, let's do it this way. Take an airplane, write the axes Z body, Y body, and X body. It is attached at the CG, it moves and rotates with the airplane. That's your coordinate system. Okay? Now, I mentioned to you before, you can define a velocity vector for this airplane with respect to any reference frame you want. Let's say this is Earth, and that's me looking at the airplane, all right? And I see a velocity of that airplane. And let's say this velocity is like this. Velocity of the airplane with respect to this person. Okay? Now, I can write this vector in this coordinate system. So I can basically decompose it into these three coordinate systems. So it would look like this, right? It would look like this. This would be the one in the x-axis. Maybe there's a little bit in the y-axis. And then I could do this, and I could say this is another coordinate system. This is another vector. So adding these three vectors, it will give me that. So I will basically call them U, V, and W. These three vectors. In other words, this V vector, this velocity vector V, can be decomposed into three components in this coordinate system. So it will be U, V, and W. In fact, in order to make it a little bit more obvious, let's put little b's here so they denote the body axis coordinate system. Okay? So this is your velocity vector, which has 3 components, u, v, and w, and they are attached. They are. If you add them together, you obtain this v, which is the velocity vector of the airplane with respect to this guy. Okay. Now here's the symbology. Here's what I would like to use in this class, and we all should agree on this. This velocity vector is with respect to somebody. In this case, it is with respect to this person, which is on Earth. So Earth is a reference frame. If that is the case, I would like to write the following. On top of this vector, I would like to write E, Earth, E for Earth, saying that this velocity is a velocity vector with respect to Earth. Okay? The second information I need is these 3 numbers are, this is written in a coordinate system because this is in the x-axis, this is in the y-axis, and this is in the z-axis, right? So they are decomposed into axes. So you need to tell me in which coordinate system you are writing this, and that comes here. And this is written in the body x coordinate system, body fixed coordinate system. The velocity is with respect to someone on Earth, but the vector is decomposed in the body fixed coordinate system. So UB is the component in x body, VB is in the component of y body, and WB is the component in z body. Is that good? Any questions so far? Yes?
Is the V body right or direction is right or wrong?
Of V body you mean?
I mean, if we are looking at top of the airplane and our wing is coming left, if our VB is right or left?
If V body, if there's a side velocity like that, which means the airplane is slightly also moving like that. So which means this velocity vector, it's a 3-dimensional picture, is a little bit to the side as well. So if you look from the top, if there's a VB, it also means that the airplane, I mean this velocity vector, this is a 2-dimensional picture, but it means V is like that, a little bit to the side. This V. We just can't see it in this 2-dimensional picture. Understand? So this V is not only coming from the, is not only straightforward, but this V is also a little bit to the side. So look up here. The airplane is not only doing this, but it's only a little bit going to the side, so it's kind of moving like this. If the side velocity is not equal to 0. If V body is equal to 0, it really means the airplane is going straight forward. But if VB is not equal to 0, it means the airplane is also going a little bit to the side because V is the velocity vector with respect to this guy. Understand that? Okay. Any other questions? These are important questions. These are very fundamental and they sound simple, but you know we have to agree on them very absolutely, so that later we all know. If I give you a velocity that says VEB, it means it is the velocity of whatever, aircraft, car, whatever, as observed from Earth, but written in the body fixed coordinate system. Clear? Okay. Now take the same picture. Take the same picture, same person, Earth, looking at the airplane. It has one velocity vector, it's the same velocity vector, same picture, okay? And let's say this is north, okay? Let's plot the vehicle carried coordinate system. The vehicle carried coordinate system will look like this. XV, ZV, which way will be y? Out of plane or into the plane? Out of plane, okay, so it looks like that. So this is YV, v, out of plane. What is this? This is the vehicle carried coordinate system, isn't it? It is the vehicle carried coordinate system. X is pointing north, Z is pointing towards local gravity vector. Look at your notes if you are getting confused. Vehicle carried coordinate system. It is another coordinate system attached at the CG of the airplane. XV is pointing towards north, ZV towards the local gravity vector, YV towards the side. Okay? But this is still the velocity of the airplane with respect to this person. It's the same velocity vector. Now, can I write this velocity vector in this new coordinate system? Of course I can. It's just another coordinate system, right? So it would be, of course, it would be in this direction mostly, right? It will be opposite to XV, okay? Some of it might be in the YV direction, and some of it actually might be in the ZV direction, I don't know. But you could say this. Let's put it here. The velocity vector, as observed from Earth, but written in the vehicle carried coordinate system, can be written as UV VV WV. It is a velocity vector observed from Earth, but written in this new coordinate system. So I would claim like this is UV. This one here is WV. This one here would be VV. Of course, you know, UV will be a minus because V is in the opposite direction, but the positive directions of these numbers would be UV, WV, and VV. Now, compare these two. These numbers will be different. This will be, I don't know, 1, 2, 3. This will be 5, 6, 8. I don't know. Different numbers. But it is the same vector. It is the velocity vector that is observed from this person when he looks at the airplane. So, E, meaning that the velocity vector of this airplane that is observed from Earth. But it is written in two different coordinate systems. One is decomposed in this coordinate system. The other one is composed in this coordinate system. But it is the same velocity vector. There is only one velocity vector that this person will observe looking at this airplane. Does that make sense? Could I write this velocity vector now in the wind axis system? Yeah, of course I can. Of course I can. I can write it in the Earth fixed coordinate system. Of course, it will not be easy, but you can. I can put a coordinate system over here. I don't know if this is north, then X Earth will be like that, Z Earth will be like that, and then whatever. You can write this in this coordinate system, in this coordinate system, in any coordinate system. But there's still one velocity with respect to this person, and that is the velocity of the airplane with respect to the guy looking from Earth. So, does that make sense? Do you understand that? Fully understand? Okay. So, I basically tell you here that V Earth, V, the velocity vector, looking from Earth, written in the body fixed coordinate system, this is the velocity, right? It is the same velocity as the other one, right? The velocity looking from Earth, but written in the vehicle carried coordinate system. The numbers, the components will not be the same. But if you would take the magnitude, it would be the same vector. In fact, if you add them, the direction will also be the same. But each of these numbers, they will be different, but it is the same vector. Okay? Good. Now, let's agree on something. I could be writing this. What does that mean? Velocity of an airplane, a car, whatever, as observed from the inertial frame, but written in the body axis system. That's what that means. Velocity of the airplane with respect to the body, written in the body axis system. What would that be? 0. The velocity of the airplane with respect to the body itself is 0. Basically, it is an observer on the airplane looking at the airplane, and he will say the airplane is still, right? So it would actually be 0, 0, 0. I can tell you right now. The velocity of the airplane with respect to the body fixed coordinate system written in the body axis system is 0, 0, 0. Because that means that the observer is on top of the airplane. He will look at the airplane and say the airplane is not moving. And then he will look at the Earth and say the Earth is moving backwards. The Earth is moving. What's the velocity of the Earth? He will say, oh, 900 kilometers per hour, the Earth is moving that way. That's the observer from the body. The observer from Earth will look at the airplane, 900 kilometers per hour, that way goes the airplane. And then you have the guy in space looking at the whole picture and says, you're both stupid. You're all moving with the Earth around the sun. Okay? Understood? Good. So, here is what I want you to agree with me. Whenever I don't write anything over here, I want to assume that if I don't write anything, that it is the velocity in the inertial frame. If I don't write anything. So if I write velocity of the airplane like this, it means it is the velocity of the airplane with respect to the inertial frame written in the body axis system. Sometimes we are going to make that assumption, and I will write it in the homeworks or midterms and stuff like that, saying that the Earth is flat and non-rotating, which means the Earth is the reference frame, the inertial frame. Or I will say, assume the Earth being the inertial frame. Okay? I will tell you that. But even if I don't tell you, and I just write it like this, it means it is the velocity of the airplane with respect to the inertial frame. So the default is with respect to the inertial frame. Is that good? Okay. So, if it's like that, we need to agree on one more thing. The velocity of the aircraft written in the body axis system, I will simply write u, v, and w, and these will be the components of the velocity of the aircraft in the xb axis, yb axis, and zb axis, and all in the inertial frame. So when I say u, v, and w, I immediately mean the velocities of the vehicle written in the body fixed coordinate system, but it is with respect to the inertial frame. Is that good? So I tell you, I give you like this, so that I don't every time, most of the time I'm going to use this, so I don't want to explain this every time. Inertial frame, body axis, so on and so forth. If I tell you this is u is this, w is this, and z is this, v is this, I want you to immediately understand this is u, this is v, and this is w. If I don't write anything over here, I'm not writing now body, if it's empty like that, it is immediately known to be the body axis system. So I can immediately could give you this. VB is equal to 210, or let's make it 0, 200, 0, and 10 kilometers per hour. And since it is like that, you could immediately say u is 200 kilometers per hour, v is 0, and w is 10 kilometers per hour. Okay? So which means you have 200 kilometers over here, 10 over here, so you add them together, this is kind of your velocity. As observed from Earth or inertial, in this case we just say it's inertial because it's empty. So when I talk about u, v, and w, u, v, and w are the velocity components, velocity vector components along x body, y body, and z body. So this is x body, this is y body, and this is z body. Okay? And if I don't write anything on top, immediately it is meant to be the inertial one. Are the velocity vector components along the, with respect to, let's write it down, with respect to inertial frame. Inertial frame of reference. Okay? As I said, if I make the assumption that Earth is the inertial frame, we should know about that, and we should write it somewhere down, and then it will be the velocities of the airplane written in the body axis system with respect to Earth. Is that okay? Good. So that's number one. Second definition is the following. CG, X body, Z body, and Y body. Now the airplane had a velocity with respect to this person, right? And I wrote it down. It was a velocity vector like that. It was a velocity with respect to an observer on Earth. If Earth is flat, it's the inertial frame again. I keep saying that. But this airplane will also have a rotation. So you look at the airplane and you will see it might also rotate, right? You are the observer on Earth, look up here. Look up here for a second. You can see the airplane is moving, yes, but you will also see an observer, the airplane is rotating. It might rotate like this. So it might rotate along the body x-axis, like this. Along the body axis. It might also rotate along the body z-axis. This is the body z-axis. So this is the rotation along the body z-axis, you see? If the airplane is in this situation, where is z body? It is here. So the airplane might be rotating around the z body axis, around the x body axis, like that. Right? So you might have a rotation, look up here, you might have a rotation around x body. And this is a positive rotation. How do you find out if it's a positive rotation? Sorry. So you take your x, you take your right hand, again point your thumb around x body, this is a positive rotation. Okay? Again, right hand rule. That's why we call it always a right-handed rule. You go from x body to y body, that's z body. That's a right-handed coordinate system. But a positive rotation, we call it like this. X body, take your 4 fingers, that's a positive rotation around x body. A positive rotation around z body would be like this. Point downwards, this is a positive rotation with your right-handed. Okay? Here, what is a positive rotation? Y body, take your 4 fingers, that's a positive rotation. Is that good? Okay, so that's a positive rotation. So that's a positive rotation, right? You go down, and this is a positive rotation. All right? So, of course, so the airplane might be rotating in all directions. Look up here again. Look at the airplane. The airplane might be rotating in all directions. But you can decompose this rotation into this, along the x body, into that, along z body, and into that, along y body. You add them together, you obtain something like that in 3 dimensions. Good. So, if this is a rotation around x body, y body, and z body, how do I show this in vector notation? So, a rotation like this can be shown with a vector like that. This is a rotational vector. So, this vector we call P. And P denotes the rotational vector, so it's a rotation around x body, and I show it as a vector. Okay? The rotation around x body you understand, right? So, how do I show a rotation as a vector? How do I show this as a vector? Now, this red arrow is not a vector. Right? It's just something I show. You need to show this rotation with a vector. And I'm showing that with this P. This P vector you see over here is the rotation. It denotes the rotation. So a P vector in this direction, and if you say this is a rotation, it points in this direction, it means it's a positive rotation in that direction. Use your fingers, your right hand to understand that. So this is, in fact, it is a vector here. Same thing over here. We call this Q. And this one over here, we call P, Q, and R. So this Q is a rotation around Y body. This is a rotation around Z body. So if you add them together, P, Q, R, these are 3 vectors. You can add them together and you might obtain something like, I don't know, something like this. And we call this omega. So omega is a vector. It denotes the rotation of this airplane. With respect to who? The rotation is still with respect to Earth, this guy. Because if you sit on an airplane, you might say it's not rotating. But looking from Earth, you see an airplane that's rotating. And you can write it in a coordinate system anywhere you want, because now this is a vector. This omega is a vector, and you can write it in any coordinate system you want. Here we are writing it in the body fixed coordinate system. And we call it P, Q, and R. P, Q, and R being the components of the rotational vector of the airplane as observed from Earth, but decomposed in the body fixed coordinate system. And we name them P, Q, and R. Is that good? In fact, because it's with respect to Earth, we might want to put a little b over here to denote that it is written in the body fixed coordinate system and this is with respect to Earth. But I'm going to make the same agreement with you, saying that if I don't write anything, in other words, if I write it like that, I will just write P, Q, and R, and they will be, because I don't write anything, with respect to inertial frame, written in the body fixed coordinate system. Is that good? Okay, so again, let's give a 5 minutes break and we'll continue.